Welcome to the SEG Europe Regional Advisory Committee's webinar series, Geophysics for Today and Tomorrow. Dr. Adriana Ramirez, Chair of the SEG Europe Regional Advisory Committee, and myself, Lori Whitesell, will serve as your host for today's webinar. Before we begin, the model for this webinar will be a short presentation, followed by an extended question and answer session. During the question and answer session, please enter your questions in the Q&A box at the bottom of your toolbar on the screen. We also welcome some questions as we progress through the presentation. Our presenter today, Dr. Kurt Strack, is president of KMS Technologies, KJT Enterprise, Inc., specializing in integrated seismic electromagnetic technology for land and marine exploration, appraisal drilling, and production monitoring for geothermal and the petroleum industry. The present emphasis is to drive the technology enabling smooth energy transition to zero carbon footprint. In that, KMS Technologies pioneers borehole to surface, and marine electromagnetics to link with 3D seismic Earth models. Kurt also serves as adjunct professor in the Earth and Atmospheric Geoscience Department and Electrical Engineering Department at the University of Houston, Maladao University in Bangkok, and at Yangtze University in Wuhan, China, where he teaches borehole geophysics and electrical methods for petroleum applications. He also teaches at other universities in China, Malaysia, Indonesia, Saudi Arabia, and Germany. Previously, he was chief geoscientist for Baker Atlas after various management positions. There he built their research and development department and supported the development of numerous new logging tools. Prior to that, Kurt pioneered LOTEM, which is transient electromagnetics for hydrocarbon exploration development, and advanced borehole geophysics technologies in Germany, Australia, and the USA. Kurt received a PhD from the University of Cologne and a master's from Colorado School of Mines. He worked over the past 25 years as consultant, university researcher, and R&D manager in the geothermal and also for petroleum industries. Kurt has over 200 publications, 1 textbook, and is an author or co-author of more than 30 patents. He received 2 Fulbright scholarships and numerous international grants and awards. His interest is integrating geophysics with other disciplines, teaching technology transfer and project development. He is a member of SPWLA, AAPG, ASEG, BDG, DGG, EAGE, EEGS, GRC, SPE, SEG, and TSEG. He was co-chair of the technical program for the IPTC in Bangkok in 2012 and is active in many committees. He was the industry representative for the IAGA EM division and still provides frequent workshops at their biannual meetings. The SPWLA granted Kurt a Distinguished Technical Achievement Award in 2003 for new logging technologies. SEG granted him the Reginald Fessenden Award for the development of through casing, resistivity, and 3D induction logging. The Russian Academy of Science elected him a foreign member and gave him the Capacitor Gold Medal for honor for his innovations to borehole geophysics and pioneering work for surface geophysics, or LOTEM. Kurt was Distinguished Lecturer for the SPE in 1998 and 1999, and SPWLA in 2004 to 2005. And in 2007-2008, he received the SEG President's Service Award. In 2012, Kurt also is a recipient for the KMS Technology Cecil H. Green Enterprise Award from the SEG. So without further ado, let's please welcome Kurt Strack.
Well, thank you. That sounds like a long story. I didn't even know that that was me. So, are many participants already there? I only see 2.
Oh yes, there are quite a lot already.
Okay, so good morning to everyone. As Laurie so nicely said, you can interrupt me. So if there are parts that you do not understand, just send her a message and put interrupt or something in front. I'm quite used to not get sidetracked. So if your question or the answer to your question gets too long, I will defer it to the end. So just leave that up to me. Our advertised lecture time is 1 hour, but Laurie has shared with me that she actually has a 3-hour slot. I hope I don't have to talk for 3 hours. My lecture, according to the slides, and I don't have any extra slides in the slide deck, is below 1 hour. So it will depend up to us what we make out of this lecture and if it goes longer. So this is the first talk of a talk of 3, and this is geared towards the European Advisory Committee, where we are trying to give presentations that are spawning interest in geophysics. So I'll try to keep this at a very low level. There are 2 more lectures, and I'll tell you in a minute what they are at the moment planned to be. If you need more details or would like to have more details on electromagnetics or Barhole geophysics, just send me or Laurie an email, and I'll consider making more lectures. I have lots and lots and lots of material. So we are talking today about electromagnetics for geothermal and hydrocarbon. And you have noticed that finally the world is recognizing that geothermal is a potential energy resource. I was lucky enough to study that in graduate school already in Colorado in the 1980s and work in geothermal right afterwards. So I'm digging out a lot of old material these days, and a lot of our customers are using our equipment mostly for geothermal. The second lecture is focused towards specific applications of electromagnetics, in this case for exploration and production. And there I will go into the details on why we are doing this, where is the success, etc., etc. Then the third lecture, which is sometimes early next year, is because we have a large student audience, and I always see people giving all of these positive prep talks to students of becoming a geophysicist. I have been relatively successful, but I'm for surely won't give students a prep talk. So I would be much more realistic what people can expect when we talk about making a career in geophysics. And hopefully Laurie will have a shorter version of what she just read. And as I said, if you'd like to have anything else, you need to let me know. I'm part of the European Regional Advisory Committee. And so I will push my own presentations second after other speakers. So let's dissect the title so that everybody that listens to this presentation can actually understand what we talk about. The title says Advanced Electromagnetics for Geothermal and Hydrocarbon Applications. So let me just use the word electromagnetics. So electromagnetics I will explain within the context of being a geophysical measurement, what it is. Geothermal hydrocarbon is the type of application. The reason why they both go together is because geothermal and hydrocarbon are looking at a very similar exploration depths of 1 to 5 or 6 kilometers. And thus the tools are very similar. I will emphasize the difference in the tools, and I will also emphasize in this presentation that your geophysical measurements are only as good as you calibrate them and you compare them to the ground truths. There are advanced publications coming out in the November issue of Interpretation, and there's a really good publication on applying electromagnetics for hydrocarbons. But when you look at it very carefully, you will see a very terrible calibration of the geophysical interpretation with the ground truth, meaning the borehole measurements. So you have to watch out for the calibration. Doesn't mean it's wrong, but the better the calibration, the better your results and the more you can trust in your results. And with my 40 years of experience in this field, I have only seen one survey where the measurements were so bad that we had to throw the data away. We've always been able to reconcile it. So I have no reason to believe that the data from anybody else is invalid. It's only a matter of we and our models are coming up with the right answer. And then today, it's a real challenge to take you from the very beginning, from basics to advanced, new application and novel technology. So I will try to do that in a very soft way. You may not even notice it, but 10 to 15 years from now, you may remember that you've heard about it and says, oh, that was really new. So hopefully that will be the case. I've taken some old slides from the SEG. These are the methods in geophysics. Gravity, you all know that what gravity is the attraction of masses, or we have a gravity wave now since 3 years, where a black hole sends out a big gravity wave, which influences the Earth's magnetic field. Magnetics, sound waves, acoustics known in the Barhole, or seismics at exploration level, or seismology in solid Earth geophysics or volcanology. And then we have electricity. And within electricity, we have electromagnetics. And I'll be talking about electromagnetics. As I mentioned before, for the black hole, gravity and electromagnetics is combined. So the gravity wave coming from the black hole is changing the shape of the magnetic field of the Earth. And that will cause some changes in it. And I will get back to that when we have the slide of those magnetic fields about 2 or 3 slides down the road. Let's look at electricity. You take a piece of rock. Pyrite is very conductive or has little resistance. You put an ohm meter on it, and you see that you have here in the slide, and I think you see my cursor, you see that you actually have some current flow. Sandstone is very resistive. There is nothing happening here. So let's replace this, since we are going to geothermal and to hydrocarbon mostly monitoring. Replace it with water. Water has little resistance, and sand, again, sandstone, and you will get the same results. So this tells you that the water, which is in every rock in the pore space, that water is conductive. Now, if you make up the rock out of little balls or pebbles, the maximum porosity you can get is 49%. So you can imagine there can be a lot of water in it. So only in fractured rocks you get very high porosity like that. So 49% is really excessively high. But the content of water in a rock can be significant. And salt water is 0.3 ohm meters, so the resistivity is very low, and there's always salt in the subsurface of minerals. So you can imagine rock can be quite conductive. Here's a combination of geothermal and hydrocarbon. We have a 3-dimensional Earth cube, and these are high-value targets for electromagnetics. Oops. This is subsalt, which is a high-value target, defining oil away from the wellbore. These are wellbores where you have sensors installed permanently. Subbasalt imaging, and on the right side you have geothermal, where you have a heat source, and that heat is essentially heating up the water. Either it generates fluid flow, which means increased water and lower resistivity, or it heats up the water, which means that the minerals and the salt in the water connects, and you have higher electron flow, which means lower resistivity. So that's the geothermal model. Now, where does geothermal happen? We have the well-known ring of fire, and those are the margins of the plates, the continental plates. And you can see here there are earthquakes. I didn't put a yellow circle here, but in Chile, obviously, there's also a lot of electromagnetics being done. The yellow circles are those areas where you find case histories of people applying electromagnetics to find geothermal resources. There are other places where geothermal is being done. For instance, you see here in continental Europe, there's absolutely no plate margin there, and you also have a lot here. This is the breaking up of the Earth's crust in Ethiopia here. So you have some here as well, but there is a plate right there. So that's where this breakup is coming from. And Kenya is here as well. Let's go to a hydrocarbon reservoir. A hydrocarbon reservoir is typically in sandstone, which is very porous. This is sandstone, and oil floats to the top. So you have oil at the top. At the bottom, you always have water. That's also known as the water lag. A lot of geophysicists don't understand those jargons that are used by the petroleum engineers. On the left side, you have a borehole drilled through that reservoir. And one of the layers in the reservoir is tight sandstone, and it seals between the top of the reservoir and the bottom. You have oil here, and because of the borehole mud that's used for drilling, you have something here called the invasion zone in there as well. And here's the water lag, and you have the oil and the water mix at the boundary and different invasion. So you are trying to determine all of these detailed structures before you produce the oil. Because borehole is usually drilled, then you set metal casings, and then you use explosives to shoot holes in the metal casing to produce only the reservoirs that you know are there. So you have to do the measurements very accurately, because if you shoot explosives in the tight sandstones, you are producing nothing. If you shoot explosives in the shales, you are producing nothing. If you shoot explosives here and there, you make the water flow up into the reservoir in the oil, and you produce water, not oil. So it's very critical that you understand where this is. And the only techniques that are used in the borehole to determine this, apart from all the other measurements that are used for other purposes, are the various resistivity tools. More about a hydrocarbon reservoir. A famous geophysicist, Nino Passalacqua, did his PhD thesis, and he found out that if you have a thin enough resistive layer, you get an anomaly, like a capacitor charge up. It's known as a capacitor effect in high school. When you remember in high school, when they open up these big capacitor plates in physics, boom, all of a sudden the capacitor could no longer store charges. So this thin resistive layer effect gives you positive and negative charges above and below, and you see this as a resistivity anomaly. This is a Barhole measurement, and hydrocarbon reservoirs are always resistive. So this is what I was pointing out to you earlier. When you see electromagnetic interpretations and they display them with the logs, check if they can really see the oil. Many geophysicists do not understand borehole logs, and they show logs that are very bad. So, advanced and new applications. The original application that's been used since hundreds of years, although the most recent industrial version was invented in the 1950s, by Kenya and subsequently further developed by Vosov at MIT, is magnetotellurics. Magnetotellurics is based on taking the Earth's magnetic field that comes in and measuring 3 magnetic fields in X, Y, Z direction and 2 electric fields. You can also measure the vertical electric field, but you don't need it. Then you take the ratio of HY and EX and HX and EY. Taking the ratio eliminates the knowledge of the source, and you can come up with an apparent resistivity that represents a subsurface. You can bring your own source instead of using the source in the atmosphere, and you can establish a signal like you saw building up here and record multiple components on the surface and get the same thing. That's called Controlled Source EM, which is a more advanced and novel technology. Here is equipment, more modern equipment, an array system for frequencies from 0 Hertz all the way up to, sorry, my mouse is jumpy. I'm not touching anything when the thing jumps. From 0 Hertz to about 40 kilohertz. And then we've recently added a borehole receiver to it, which allows you to measure EZ and the magnetic field in the borehole, in particular for monitoring seismicity and doing better imaging. So this is a picture of an advanced system. So let's go on and ask us questions. What are the targets for these methods? And as the title said, geothermal. In geothermal, we are looking for low resistivity, which means more water or hotter water. In hydrocarbons, we are looking for low resistivity secondarily and high resistivity primarily. The reason why high resistivity is listed second here, because high resistivity is the oil. If oil is resistive, as that meter showed us in the beginning, there's no current flowing. So high resistivity is inferred from the charges at the interface. So if you have a thick resistive reservoir, a thick resistive carbonate sequence, let's say 150 meters thick, you will not be able to get through that with electromagnetics. It will act as shielding blanket and not as capacitor. If it's thin, you can see it. In mining, and I have to bring this because we need to put ourselves in the context of the rest of geophysics. So in mining geophysics, we are looking for low resistivity minerals, and environmental geophysics, we are looking for low resistivity contaminants. I have two cartoons for that. This is the one for the minerals where you're looking for low resistivity. And the methods you use for that are slightly different than what I'm presenting here today. And the same with environmental geophysics. You are looking for low resistivity and seepages like dam leakage and so forth. However, monitoring arrays could be equally applicable. What is the status of the various methods? As I said before, Magnetotellurics was developed in the 1950s. It is here to stay. It made it through many of these downturns. There are three major and several small equipment manufacturers, but the market is very, very small. Controlled Source EM is essentially audio magnetotellurics, which started in the 1970s. There they use the same interpretation as in magnetotellurics, so you get less sensitivity as using the controlled source. And then there is low temp, where early commercial work was done in the 1980s, and we are revisiting this. In fact, to give you an idea, the transmitter, my transmitter, is built by an engineer who has been doing this for almost 40 years and is close to 80 years old. And he was telling us yesterday that he needed a young guy to help him because he had these difficulties operating the mouse because his fingers couldn't feel it anymore. Then, of course, there's induced polarization. Induced polarization is big in Russia and China. It was not successful in the West except for mining and environmental applications. There is a lot of room for misinterpretation, and I leave it with this. You have to ask me questions if you want to know what I mean. And then there are dipole-dipole measurements, which are DC resistivity measurements. They work very well. The problem is that the distance between the dipole is many times larger than the depth to your target, which is about 3 kilometers. And then you do not know where the information comes from. So it could be very ambiguous. The total market for all of these methods is small, and it's too small for any big companies to get into it. So every time there is a downturn, electromagnetics is the first to suffer. And we have many exotic seismic methods that are suffering during downturn. Example, shear wave seismic. How do we integrate these targets? We use electromagnetic energy, and I've said already, magnetotellurics and controlled source, natural or man-made. We measure the electromagnetic field, and this is important. We need to understand the physics. There are all the time commercial companies running around, and there are several in Texas, and I have no way of catching them. And some of them have been around for 20 or 30 years, and they still find customers. Their physics is wrong. You need to understand the physics, and you need to be able to verify your results with 3D modeling. If you can't model your results, don't believe it. Our physics and our computer modeling, yes, it's complicated. Yes, it takes a long time. It's hard to put your hands on it, but you can do it. If you can't model it, don't believe it. There's something wrong in the physics. Physics is always right. What's wrong is the brains of the geophysicists, not the physics. And you need to measure the right components. Unfortunately, because of the success and the strengths of the electric fields, a lot of people are only utilizing the electric fields and controlled source electromagnetics. That's like Russian style tooth extraction, when it takes 3 months to extract the tooth because the patient isn't allowed to open his mouth. You can do a lot better than that. The volume focusing is in the magnetic field components, not the electric field components. So you need to mix the components and use the right components. And I've said this before, you must calibrate your measurements. If you cannot calibrate your measurements against ground truths, if you don't have a borehole, there are other geophysical measurements. There is geology, but you must calibrate your measurements against the ground truths. You know, when you get as old as me, then you know that sometimes you get 10, 20 years after the work was done, the answer. And I can only say that what I said before, only one geophysical survey produced bad data that I have ever seen. And people always blame it on, oh, these guys and these guys. It's not that. They may not, some of these guys may not speak proper English, but most people are doing good and decent work. So the methods I'll introduce to you today are 3. Magnetotellurics, which is land-based and also marine, controlled source electromagnetics, and marine controlled source and magnetotellurics. I will mix in some case history, so it's not all methodology. Remember, these case histories I mix in are only summaries. So simply the presentation and the lecture doesn't get quite as boring. Magnetotellurics is a passive method. And where does it come from? We have activity in the sunspots, and the sunspots have outbursts, and these outbursts send electrical particles towards the Earth. The Earth has a magnetic field, and these particles deform the magnetic field. And in a minute, I'll show you what is happening with these magnetic fields. First, you have the magnetic field, then you have the solar flares, then they bend the magnetic field lines, they get together in the, on the backside of the Earth, and when they get together, the current flows. And this current can go up to 100,000 amps. It's far away in the ionosphere, so we'll see on the Earth a plane wave magnetic field as it comes in. So this is the, oops, again, magnetic field, the plane wave magnetic field as it reaches the Earth. That's why we always make the plane wave assumption. And my diagrams have this sinusoidal wave hitting the Earth. So that's where it comes from. You can also see on this, if a gravity wave hits the magnetic field, it will also deform it and change the shape of the magnetic field. And guess what? The variations are the same frequency as the magnetotelluric source field. So that's why LIGO, which is the Laser Interferometry Gravity Observatory that detected the gravity wave and the black hole and imaged it, that's why they are using our sensors to image the black hole through the variations of the magnetic field. Then for lower frequencies, that is also used for mining or environmental applications. We can use in the mesosphere, in the weathering layer, the lower 30 kilometers, the thunderstorm activity or lightning strikes. And this is a distribution from NASA, and you can see around the equator, you've got quite a few of those, and that is our source field for them. Obviously, it's beautiful to have lightning, but you can imagine if a lightning strike hits your electric field sensor, even lightning strike protections will not protect you from a direct hit. Your equipment is toast if it gets hit. And again, we have the same diagram as before. Here is the plane wave source field. These are the sensors, and these are the quantities we derive. Oops. And these are the quantities we derive by taking the ratio of E over H multiplied with the frequency. So we get a resistivity in XY direction and one in YX direction. If they are the same, the Earth is layered, one-dimensional is what we call it. If they're not the same, we have a boundary like this here, it's two-dimensional. And of course, there are indications for them to be three-dimensional. That's what we use actually the vertical magnetic field for. One quantity to remember, and we look at this a little bit more when we look at the marine CSEM later, is the skin depth. The skin depth is essentially the depths at which the incoming electromagnetic energy is decayed by 66%. So we have low frequency goes a lot deeper. So low frequencies are used for deep applications, and high frequencies go a lot shallower. So high frequencies you use for shallow and low frequencies for deep crustal work. And there are different sensors for the different frequencies because of the stability and the way they respond. And the skin depth you can remember easily as 500 times the resistivity over the frequency, the square root of that. And so when somebody says you want to do something at 10 hertz, you plug in your 10 in here, you say you have 10 ohm meters, so it's the square root of 1 is 1. So at 10 hertz, you have a skin depth of 500. So a 10 hertz signal at 1 ohm meter resistivity, which is typical for the Gulf of Mexico, ocean front, frequency 1 hertz, you get 500 meters deep. You have to go to higher frequencies to go shallower. So the skin depth is a very useful quantity. Then controlled source EM, in this case low-tem, you send a signal, which is a square wave like this. Every time you switch, you generate a decay, just similar to one of these daily changes of the coronavirus curve you see on the Johns Hopkins website. So this is a well-behaved coronavirus curve. You have an outbreak and then you have isolated it, and after the isolation it just goes down like this. So if you get additional bumps, then you've done a lousy job and you get an additional transient. So these things add up. We actually have patents on how to find those and compensate for that, but only for electromagnetic applications, not for coronavirus. So you send this out, and then with time, increasing time, the signal goes downwards. When it hits a layer boundary, it also goes outwards. And then at the surface, you measure in each of the fields, you can describe the subsurface completely. In the next diagram, I'll show you some 2D sensitivity functions. And we have the same thing. We'll send a pulse, and you'll have to watch it because it's animated. So I explained it before I started. You'll send a pulse, and then the energy goes down, and you just watch it. And I'll say a few words when you go there, and I'll probably run it twice so that you can actually see it. So here you have a transmitter and receiver spaced at 4 distances. This is at each of the distances. They're all different. Notice here that most of the energy is directly below the receiver. Here, there, and here. This was actually calculated by Roland Martin. I apologize. I think the reference is under the picture. The other part you notice that at the same time, on all of these, you see the same depths. This is something which people have a hard time understanding. For time domain EM, the offset, the distance between transmitter and material, has no relationship with the depths of investigation. That's, by the way, if any one of you ever looks at my book, that's wrong in my book, and that's where the late Brian Spies won the argument with me in 1989 publication in Geophysics. But here you can see it. Again, this is the last time I run it. And it goes down with offset at the same, so you can see the signal instantly. And this means they are, in terms of coronavirus, that we have not controlled the outbreak. It starts instantly. Of course, you want to control it. You want to have a low-pass filter and want to have this transient rise very slowly. So at the same time, the information comes from the same depths irrespective of offset. That's key. That's only for time domain EM. There is some bias towards receiver location. I'm trying to be very careful. You can see here, there's more energy directly under this receiver, there, and there. So those are the key elements. Now, in marine magnetotellurics, we have again the electromagnetic field coming. It goes through the ocean. Also, you have it on land. You have a thin reservoir. And this has been drawn by Scripps. And this is for a thicker reservoir. This doesn't show you the thin direct hydrocarbon indicator effect, the thin resistive layer effect that Arminio discovered in his PhD thesis. Because you have charges on both sides here, and this is just a normal capacitor effect. The energy is being carried through the reservoir with these charges at the boundary. And you'll see then the response of this at the surface. And the secondary response is what you measure on the ocean floor with your receivers or on land. There are serious challenges. And the biggest challenge is to find thin reservoirs. How do you do it? Onshore, you do the same thing as you do with the coronavirus, except that we call it look at the sensitivity by looking at the Jacobian, which is the first derivative. You click on John Hopkins of daily variations, and you can see what's happening there. And here you have, take the reservoir and you take the variations for the thickness of the reservoir. This is the magnetic field. This is the electric field. And you can see that the normalized Jacobian has a stronger response in the electric field. And the magnetic field with time, damn coronavirus cough. Anyway, I won't infect you. Actually, I don't have it. So you see nothing in the magnetic field. And here you have the reservoir influence. This is actually from a reservoir from southern Germany that we are not even allowed to talk about. That's onshore. And so CSEM is the closest direct hydrocarbon indicator to find resistors in conductors and find oil. When I was a lot younger, I used to always respond with a very strong nonsense because it's not a direct hydrocarbon indicator because we use the boundary charges. It's an indirect, but it is the most direct hydrocarbon indicator geophysicists have to see the resistive fluids. There is no electrons jumping from water molecule to water molecule in high resistive oil. You have to have sufficient water in it to have that happening. So it's important. going in the wrong direction. And so now we go to challenge number 2. Anisotropy. Every layered Earth, and since the Earth was built by deposition of rock material by the ocean going in and out and making layers, we have layered everywhere. And so we have anisotropy, or to be exact, transverse isotropic, which means it's the same in horizontal direction but different in vertical direction everywhere. The error due to anisotropy is at least 25 to 50%. So if you see electromagnetic interpretation without anisotropic models, good luck. Unless it's salt dome or some crystalline rock, but if it's sedimentary basins, it's wrong. The interpretation is wrong by 30 to 50%. There's nothing they can do about it except calculating anisotropic models. And this is why. Here we have reservoir scale, which is about 25 meters. Red are the sands. These are electrical resistivity image logs. So you put a button and inject the current in the borehole. And these are thin layers, up to a third of a millimeter thick. The darks are the shales. Shales have a lot of water in them. They are conductive. The sands are resistive. So the oil is in the yellows. And of course, at reservoir scale, the Earth is anisotropic because of this layering. At logging tool scale, which is 2.5 meters, the Earth is still anisotropic. At lamination scales, the Earth is still anisotropic. And then we go to a scanning electron microscope, 2.5 millimeters, we still have this layering. And this is because that's how the deposition works. So anisotropy is everywhere. 3D anisotropic models are mandatory. So the next example shows you a data set and from a commercial logging contractor, and we have a log and the interpretation on the left. These blocky curves are the inversion results for the vertical and horizontal resistivity. The jagged curve is the borehole log. This goes all the way down to, I have to put reading glasses on to read this, to 2,000 to 3,000 meters at the bottom. And on the right side, we have the typical borehole logs. This is the gamma ray, which tells you about shale content. These are the resistivity logs. You see the vertical resistivities are higher, that means more oil. And on the right side, you have the oil saturation analysis or the sand shale analysis, and you get the oil saturation from the vertical resistivity in orange and from the horizontal resistivity in red. The horizontal resistivity would be a standard induction log. The vertical resistivity comes from a 3-component induction log. In this case, there is 42% more oil by just measuring the vertical resistivity. The lowest improvement I've seen from any one of the two logging contractors that have this tool is 20 to 25%. Most logs, and not many are published because this is very, very valuable information and confidential information. Most logging contractors have improvements of 30 to 50%. Let's go to equipment. I'll say a few words about a high power transmitter for land, transition zones, and marine. An array EM receiver for magnetotellurics and controlled source. I've cut this down significantly. So here we have some pictures of a 200 kilowatt transmitter in China. You see this little box here. So since it wasn't fully on the picture and I didn't want to change this picture, I put that box that you see here on the right. So, and this is an older one from 1980. This is a 200 kilowatt. So this was sometimes 15 years or 10 years after that. That's in South Africa, 100 kilowatt transmitter. This is in China, and this is in the Imperial Valley, California. We actually found the Barhole field during this survey with this transmitter in 1980, 81. Next, we see a marine transmitter. This is EMGS's marine transmitter. I guess the acknowledgement to EMGS is missing. This is their towfish for the transmitter. And the cable is right here. We'll see a picture of that later. These are the receivers as they throw them overboard for the marine environment. These are 5 of our land systems, different land systems for different purposes. This is the one the USMT array uses for crustal applications. This is a mixed one that universities can use, and a standard commercial broad one all the way up to all these components. Now, a new array system would acquire EM data or MT data in a grid box like 3D seismic. Here you have a bin, which in this case is 5 by 4, 20 stations. Only one station has all magnetic field components. The other ones only have electric field components. And since the magnetic field doesn't vary that much spatially, you would just duplicate those components and you have a bin here. So that's called a 3D array. These are helicopter-borne sites on mountainous areas like in the eastern US, the Appalachians. And these are standard 2D lines like they're used anywhere where you have all components. And the system will come up in the next one. We have seen it, so I will go quickly through it. This is high and low frequencies, are high frequency coils, low frequency flux gate sensors. These are different sensors. From flux gates, they're very small. Where is a small flux gate sensor? This is actually a big flux gate sensor. This is also big. This one previously is smaller. This one is a little bit bigger than a quarter. That's the one we use for our Barhole tool and marine tool. There's the same flux gate sensor in our marine prototype. And there is a flux gate sensor in the Barhole. This is the marine receiver from EMGS. You see the magnetometer. Here's one, there is another one, and here's another one. The electric fields are coming out here. I won't say much of those. Those bubbles here are for buoyancy, and the anchor here gets essentially released on an acoustic pinger, and then the damn thing floats up and you pick it up when that happens. So in an array system, we were able to standardize the acquisition. And I don't know if you see me, but man, I'm sitting in my office and it's on the same floor where my son has his bedroom. The air conditioning is cold. I have to wear a blanket. So anyway, we've standardized the Magnetotellurics and the CSEM and the marine CSEM, that we can use the same hardware, which is quite complicated. We use the same hardware for EM and the methods and seismic. And now I think the University of Cologne has even been able to do with time domain data, frequency domain processing and inversion, and they're getting very, very comparable results. So it's taken us many decades to get there, but more and more we are getting things to a point where the systems become simpler and better understood. Here is a data set where you have at the top electric fields, at the bottom you have additional magnetic fields. So this is a system where you had an array laid out with multiple electric fields and only one side with the magnetic fields. This one is from northern Germany, this data set. Originally the data is noisy, and then you use robust processing to make this data smooth. These are apparent resistivity curves that are looking at lower frequencies at greater depths. So here you actually see the separation between the curves is when you start seeing a salt dome. We've talked about these apparent resistivities before, and let me just say that the apparent resistivity is 0.2 times the frequency divided by the electric and magnetic field. And if they're same, it's one-dimensional. If they're different, it's 2- or 3-dimensional. This is a data set from Hawaii, obviously for geothermal. And And you can see you have 1, 2, 3, 4 decades of data. This is the data itself. I'll give you an example from some subsalt imaging in Germany, where we are looking at a salt dome like here, and we are looking essentially, this being the resistivity contrast. This funny thing is supposed to be the incident Earth magnetic field. And some of you may notice there's something wrong with this diagram, but I leave that up to you. So the original model had only a salt dome and seismic data, and now you'll see the seismic data in a second. And they didn't really know where the salt dome was, and they wanted to site additional wells to find more oil, because they already had a producing platform, and in Germany getting permits to drill is very difficult, and they had to drill from the same drilling platform and somewhere underneath the salt dome, so they needed to image it correctly. These are the MT sites, and this is the overhang as it was imaged after the MT survey. I need to say it's an integrated model, so it includes gravity and seismic and magnetotellurics. And the improvement after this on the seismic data for the pre-step depth migration is shown here. And I hope you see that this is the original salt dome, and you really didn't know much here. And this is after the MT survey. You get a lot more detailed information, because you can tie down some of these boundaries. And there was a new well drilled here which confirmed all of that, and is of course producing. So this should have a reference, Henke 2020, it comes out in November. Here's the animated model of 3D animation from the 2D sections, the seismic sections and the MT-N1. And notice that you can see this overhang. In this case, the MT sees this overhang. The gravity, the second derivative of the gravity, sees the white outline of the salt dome. And the flanks are seen from a combination of gravity and magnetotellurics. There's more to the interpretation of it, but I don't think that's part of this lecture. Next, we go to North Dakota, where shale gas and oil is very important. We're going to the Bakken, which is mostly oil. And all of you know about the shale revolution, started pretty much there. We have at 10,000 feet reservoirs, 3 reservoirs, the upper, middle, and lower Bakken. And they're now producing even from the 3 forks at 10,000 feet. These are very thin reservoirs. The middle Bakken is only something like 10 meters thick. These are the anisotropic models derived from the resistivity log. And you derive those by calculating something which we call cumulative resistance and conductance. And each time these curves break, you have a layer, and then you use those layers to derive the models. And if you take this to monitoring, you would add Barhole receivers and horizontal receivers in the wellbore to this. So we just did an experiment, and in fact we sat on the data for a year, because I thought you're not going to see any 10-meter reservoir at 10,000 feet. And then when we ran the model, we said, shit, very strong response. And I have the anisotropic results here for the horizontal resistivity and the vertical. And the variation is 3 to 6% after reservoir depletion. So you calculate 2 models and you take the difference. And 3 to 6% is well above the resolution capability of the method. I mean, 2 to 3%, I would stop standing up for it unless I have a log and it's true. No, it's true. But 6%, 5%, and I've seen cases, real reservoirs in Asia of 20 to 40%. So the next one shows you what's happening in the reservoir. In the next slide, we have an animation. We have a transmitter at the surface, and the transmitter has one leg here to the leg going to the left, and this is the reservoir outline, and the reservoir is getting depleted, and you can see how the current is being channeled with time into the reservoir. Now, if you look at these numbers, these are volt per meter, and you can essentially measure it in the borehole. You can multiply these with your sensitivities and everything else, and you will find out that you are well within the millivolt range. Because this is a transmitter is 1, and the usual transmitter is 1,000 meters long and uses 100 amps, so you already have 10 to the 5th. So this being 10 to the 8th or -8, you already have 10 to the 3. So it's significant, strong values that you can actually measure easily. So from this, we are now going to the last method, which is marine, and you can, while you're still watching this video. And before we go to marine, we are going to go back, and we are going to look at the skin depths again. And this is the normal formula for the skin depths. If you plug in pi, and this is not a pi you buy at the store, this is actually 3.14, and 4 pi 10 to the -7 for mu naught, then you end up with 500 times rho over F. We've said this before. And so we have here again the 1 ohm meter and 1 hertz that we had before. And this, I guess, is a slide that I stole from EMGS or something. But I say the amplitude is reduced by 66%, and they say to 37. Well, half a dozen one way, 6 the other. So skin depth increases with decreasing frequency. Skin depth increases with increasing resistivity. This is very important for marine EM. So in marine EM, where you only use one frequency, you are using multiples of the frequency. You know the resistivity of water is 0.3 ohm meters. So in water, the skin depth is 548 meters. So this is why for marine CSEM, it works best in deep water, which is deeper than 600 meters. Shallow water is below that 1 skin depth of normal seawater. That's when you would use marine time domain, not frequency domain. But that's a different story. That's not part of this lecture. If the overburden is 1 ohm meter, which is typical for marine sediments, they're lower in resistivity than terrestrial sediments. Or the overburden is 2 ohm meters, the skin depth is 1,000 meters or 1,440 meters. So why does marine EM work with one frequency? This is the one frequency. Everybody talks about sine waves. Well, you don't use a sine wave, you use a square wave. And from digital signal processing, when you use a square wave, apart from you can make a square wave easier than a sine wave. A perfect sine wave is difficult to generate. So you get through this step also the harmonics. So you get the base frequency of 0.2 hertz plus all the odd harmonics. So these multiple frequencies help you to investigate an image in the Earth. So you have here 0.2 hertz, and we use the same formula we have before, and you go relatively deep. Then you go to higher frequencies, and then you go to even higher frequencies. So you image by using the multiples from the spectrum that you get from a square wave. So it's very easy to make a system like this. How does marine CSEM work? You put these landmines on the ocean bottom. Oops, they're not landmines. They are magnetotelluric or CSEM receivers. And you drag a transmitter across, and you have a hydrocarbon reservoir. So for the electric field, the scaled electric field magnitude versus offset from 0 to 10 kilometer. So here the source is directly above the receiver. So this point would be right there. And then these would be to that side. And this is the phase. I won't say much about the phase, gets too complicated this early in the morning. So here's a magnitude versus offset plot. And now you watch this boat running across. It goes over the receiver, there over the receiver. We've picked two of them. It goes up and then it goes down. And then what you do is you find a reference receiver where you know you have no oil and plot it on the same scale. And then the difference from that reference receiver is your direct hydrocarbon indicator. So here we take the reference receiver from this area. We know there's no oil. We flip it and we plot it here. And this is your direct hydrocarbon indicator. You see how beautiful you can see this? Now, everybody again looks at the Johns Hopkins website and knows that the daily change of the coronavirus shows you the characteristic of the damn thing per country. So you take the derivative of it, or you take the derivative of the derivative, the second derivative. You can actually do an edge detection of these reservoirs and can see multiple reservoirs. So, it was good. I put the courtesy here. Let's go back to geothermal. And some of you who have listened to me before are expecting that I talk about a nice integrated case history from Europe. Nope, not going to do it. I talk about something one of my colleagues did from Thailand. Using our system, they have two geothermal areas near Chiang Rai in northern Thailand, the Phang area and the Mae Chan area, and they measured 33 sites. It took 2 to 3 weeks, and they had in right next to the bridge over the river Kwai, a remote reference site. Mahidol University has a campus there, so that's where they have the remote reference site. And they drilled it. So this is the equipment in a rice field. And the publication reference is under the color scale, I apologize. This is their 3D inversion results, and they see multiple targets. They are dissected in the next diagram, where they find C1 target, which is less than 100 depths from the AMT measurements, the high frequency measurements. And this is a hot water, shallow hot water target for springs, hot springs. And the deep target, potentially a geothermal reservoir, is less than 750 meters. And so they were very pleased with this particular survey. It was nice for me to watch this from the beginning when the Ministry for Water Resources started talking about geothermal until they finally did this, which took about 10 years or so. So it was a very interesting experience. In summary of this presentation, I reviewed surface EM method, magnetotellurics, and CSEM. I mostly talked about land. I just talked marine about the method. Both are key in exploration, production, and monitoring for geothermal and oil. In fact, in geothermal, EM is the first geophysical technique. Seismic is only now being used more frequently. Calibration is always needed. The challenges are anisotropy and thin reservoirs. And equipment that's important is array systems and high power transmitters. And if you are interested, send an email and we will see if we can get some other subjects covered. From Barhole, how we look at the different logs to other AM applications. So we see the future that we will acquire more data, denser data, seismic and EM. And EM will be more frequently used for monitoring. There is an increase in it, but in many cases, people don't go past the feasibility or the initial trial because it's a new technique. We also, in most cases, recommend not to use the technique when it gets too risky, because the initial effort should be really successful. So we're still very careful about applying it. We only go after very sure cases. And then the industry downturn comes and kills the most exciting projects. Integration of surface with borehole is essential, and we also need to integrate land and marine. With this, the lecture is done. I just want, if some of you want to know more about the commercial value, I've put this diagram in it, but essentially I tried to focus mostly on the technical aspects in this. Thank you.
All right, thank you very much, Kurt. We have our first question for you. EM struggles with stacked layer responses for hydrocarbon detection. Is this also the case with geothermal mapping?
No. As I said, stacked layer responses, in particular in the marine environment, you can deal with by looking at the second derivative. And there is a publication on this, which the chief engineer of BGP wrote. We actually worked on that together, and he wanted to publish it. But you can see stacked responses. I just have a problem with advertising that when you don't have dense data, because presently the spacing of the data is 500 to 1,000 meters, which is bad. In Germany, the data was so successful because the spacing was 50 to 100 meters. If you have data redundancy, you can easily stack layered responses. But if they are resistive, they are more difficult. In geothermal, the targets are conductive. And if you combine it with seismic and other techniques, you should have no problem getting them. If you think that EM alone will see the stacked reservoirs, my answer is think again. Because with conductors, the most thing that your signal responds to is the integral value of volume conductance. So you really need to constrain that in order to separate the stacked reservoirs. But once you can constrain it, you're in business, you can see it.
Okay, thank you.
With CSEM, sorry. You can see it with CSEM. With MT, it's more difficult. You can also do it with 3D modeling, but it's more difficult. But with CSEM, it's easy because you have time separating the depths from each other.
Okay, thank you. We have another question. Is EM the best tool for geothermal exploration as seismic is for oil and gas?
You know, when I was teaching at a university, I would probably answer that question with yes, but the reality is all a function of money. If you are going to put money after geothermal exploration, you will always want to do also seismic. There's nothing as good as seismic. And EM is essentially, I have a cup here. And you can't, I don't know, my camera is not on. Why is my camera not on? Anyway, I have a cup here. EM sees what's inside the cup. And I put vodka in this morning. Nope, it's just sparkling water. And seismic sees the outside of the container. So you want to combine both of those techniques. If you don't have the money, EM is the best method. EM is the first method if you look at the industry and the applications over the last 40 years developing geothermal resources, because it's more cost effective. But if cost is not an objective, you use seismic. Germany uses seismic, but they have a very strange understanding of geophysics. So everywhere else, EM is used more, but it's not necessary. I would use both seismic and EM together.
Kurt, I guess this is the same for offshore mineral, rare earth material exploration, where EM has been used mainly, but I guess it's the same reasoning, a matter of money.
Oh, Adriana. Okay, I'm going one slide back. Let me just give you an answer to that's interesting instead of giving you an answer. Look, EM should only cost 10% more than seismic. There's no reason to not do EM when you do a seismic survey. The problem you have is that EM costs almost as much as seismic offshore, and it's high value. EM works very well offshore. So that's why people do this and that, but that's every time in the beginning of new techniques. So,
incoming call from 281-404.
I'm sorry about that. I can't stop this girl talking. So this is 100% of the value. No, 100% of the cost. This is 100% of the value for an asset, a hydrocarbon asset. So surface methods. And Adriana, when you remember your days in an oil company,
Kurt?
calibrations, which means you can do repeat measurements, 4D measurements, add another 20%. And semi-permanent, and I have calibrated this in terms of what we talk about as geophysicists, reoccupied, recalibrated measurements, another 20%. And these are permanent installations. So if you go and do all your geophysics permanently, you have 20% of the cost from 100 to 80%. So you're installing all your sensors in the very beginning permanently, but you're getting 80 to 100% of the asset value. So your question is immaterial. We are developing our assets incorrectly by doing all of this geophysics, because geophysics is mostly an exploration here. This is well logging, which is also part of geophysics. This is some integration geoscience. This is 4D or DAS coming into place, but these are permanent installations. So for very little money, you're getting most of the asset value. So we have to change the way we are approaching exploration. We have to do it environmentally responsible with a minimum carbon footprint, and as much as possible CO2 neutral. And you can only do that by reducing the cost by 80%, but getting most of the value. So whether you do seismic or EM becomes immaterial, because I can make a seismic sensor and an EM sensor combined, and the cost is immaterial, because most of the cost is in the operation of the equipment, not in the equipment, not in the technology. The problem is we don't understand it that well, and we have markets, we have a geophysical data processing industry of multi-billion dollars. Any single brilliant geologist can beat the whole multi-billion-dollar industry. Looks at the data, says this is the result. Obviously, we don't have that geologist very often. So, Adriana, marine, it's the same thing as land.
Oh, no, yeah, but I understand that. I was just, my comment was about rare earth material exploration offshore, not about seismic or oil and gas.
Rare earth material.
Okay, I mean, that was a different topic. So
rare earth
anyway, I am with you with your answer, and thank you.
Yeah, you would use the M for rare earth materials.
Yeah, it's mostly, I mean, it has been more used. Of course, seismic is useful, but it's also a matter of cost in that case.
Yeah, but then again, they drag the receivers on the ocean floor. You can easily add both of them to it. I don't understand why people have an opinion about whether they use gravity, seismic, or electromagnetics. They want answers, not showing off their own technology.
Okay, we have other questions. The next question we have spectral methods been explored using this type of data to also estimate the depth of the source?
Well, that's depth of the source is not the right term in electromagnetics.
Incoming call from 805-570-6108.
I'm sorry about this. This was actually a former SEG president. He never calls, and now he calls in the middle of the webinar.
No worries.
So the source is at the surface because it's safe. You can put the source in the borehole. Some people do it. It's not safe. So The source is not in the subsurface somewhere. So it's not like an image source. You can do imaging with the source. It's not a very good method. It gets very inaccurate. That's a virtual source. The other source is in the atmosphere, which means in the ionosphere, far away. So the distance of the source you can add. You can add the distance of the source by calculate the distance of the source for a controlled source by taking different offsets, and then you can determine how far away the source is in case you have done a poor job or the source is in a mountainous area or in the desert and you really don't know where the source is. You can do that. My old teacher, George Keller, once was very proud because they were screwing up in the survey how they could find out where the source was. But, you know, you should really know where the source is. So I'm not sure I understand the question is what I'm saying.
Okay. We have other questions. So for volcanic high temperature geothermal systems, what is the signature of the reservoir? Conductive or resistive?
Conductive.
That was easy to answer. All right.
Well, there is an anomaly. When you have very high mature mineralization, like some shallow reservoirs in Iceland after volcanic activities, they can become resistive or have resistive mineralized zones around conductors. But it is very, very rare. I have only seen one reservoir like that and only a small part in the reservoir, whereas most of the heat sources were very conductive.
Okay, great. Thank you. The next question, I would like to ask if you have any comment about the casing effect in the Bakken example. Also, if there is any comment regarding EX and EZ onset arrivals. Thank you.
Okay, those are very convoluted questions, and I can give you a whole lecture of the casing effects in the Bakken. We actually have, there on our website on the publication space, some small nuggets of calculating casing effects for reservoir monitoring. We can actually build the tool and already have the sensors to do that. But we don't have the funding, so that's why we don't talk about it. So we talk only to a limited extent about when we have the funding, we have to do patents and build the damn thing. But you can measure through casing, and in the Bakken you can do too. Nobody else can. We are the only ones that have the sensor. So this little marine sensor I showed you, that is also the sensor that will measure through casing at the right frequency. We have done the 3D modeling and the feasibility to account for the casing. I'm not sure that any other models that are out there are correct. They're getting slightly different results, but we are getting the same results we did when we built the through casing resistivity tool. So I'm very confident that our results are reasonable. So you have to build a tool in order to account for the casing effects in the Bakken. The tool doesn't exist yet. Our shallow borehole tool is shallow, 32. We're now making a 100-meter version. So for a borehole tool, it takes millions of dollars and a few years to build. Then you can do it. You need to measure, when you measure through casing, also the magnetic field. And that is much, much more difficult. Electric fields are easy to measure. Magnetic fields are much more complicated to measure. And that's why I said nobody has a sensor. We have the sensor. So can we build a tool? Give me $10 million and you have a tool 3 years later. So now you're no longer interested. So the next question of that question was what? Those were two questions in one.
Yeah. The second part is also if there is any comment regarding EX and EZ onset arrivals.
I understand the X and EZ onset arrivals. You really don't have onset arrivals for those because you are not looking at it in terms of propagating wave equation because it's diffusion. You do need, by looking at casings and imaging directly under the receiver, extremely accurate measurements for EX at the surface because you need to measure EZ. EZ images directly below. EZ is essentially the current that flows up vertically below the receiver. And you need to measure that accurate. If your borehole is not perfectly vertical, the only way to correct for that is by measuring EX at the surface. So you need to measure both of those. There are several publications to that effect already out there. People have realized and noticed that that's important. And that's the main reason why we built the shallow borehole tool. So a 30-meter EZ measurement is worth $1 million. It's better than any surface measurements because it images directly below the receiver. That towards EX and EZ. Onset associated with it. In the offshore environment, you can plot electric fields like seismic and look at onsets because you have the water wave and the air wave separating from the reservoir wave response. But anywhere else, you can't really talk about onset. So,
Okay, we have additional questions. In magnetics, I think they're clarifying it, their question. In magnetics, for example, we use spectrums to determine the depth of magnetic causative body. In the EM method, spectrums of the data have been used, for example, to improve the 3D modeling, to invert to depths and the data. Or how do you invert to depth for the data? I think that's what they're asking.
well, you know, magnetics is equivalent, so you can't really distinguish all parameters of the model. Electrical methods are not equivalent. You have some ambiguity that is caused by equivalent models, but so once you have a model, you have a depth. Your model includes the depths, and you can invert the depths and add certainty and uncertainty and error bars to it. Every measurement has an error bar. The way we do it, that with controlled source, we look at the 95% confidence interval and
Incoming call from 281.
a 95% confidence interval. And then with that, we bias it. But the important part is what constraints do you have? What part do you know? What do you not know? If you know any of the layer boundaries from the logs or from seismic, you fix those. And you put all of your inversion energy on the parameters of the medium, which are the resistivities or anisotropy, or if you're going for permeability. You can also go further for petrophysical parameters and try to match those with the log. So inversion is a model that the geophysical brain generates. That means you have a model, you calculate the response, you compare the response with your data. You keep changing the model until it matches your data. So depth comes along with the model. The more you have fixed your depths, the more your confidence you calibrate it against real logs. That's why the borehole calibration is such a high value. It gives you confidence. Even if you can match your logs and core measurements and your seismic doesn't match, and the exploration manager has to make the decision where to drill, he's not going to use the seismic. If he's an inexperienced geophysicist, he will only use the seismic. So,
Okay. I guess we have a question. They want to know what your thoughts are about full waveform inversion type methods for CSEM.
they work. They are still in its infancy. They are a lot further than they were 40 years ago. 40 years ago, my EM colleagues would kick my ass when I would always push some PhD students of a seismic guy talking about the stuff. That's what Bortfeld at that time, the professor. And they gave presentations. Today you have the group around Delft the professor there was actually one of the, we tried to get him as postdoc a long time ago. They work, but we haven't really been able to interpret data with it correctly, because this whole concept of physics guiding us in what part of the signal we use. So you look at some of our transients that rise very fast, and you look at the daily change of the incidence in the coronavirus. And you see that they're trying to push them down to rise very slow. So they're trying to apply a low pass filter as much as you can. So this is the type of information that in particular in any type of waveform inversion is very difficult to integrate, which is the physics. Which part of the reservoir is important? You notice in my plots, I always look at which part of the signal actually interests me, because we can always screw up the whole data by over-filtering it. I really apologize for all of these interrupts, but I have my phone line so seamlessly connected, because I need to be connected anywhere in the world, that they all keep ringing at one of the devices. I'm sorry about that.
No worries.
I keep pushing them away. And then, of course, I shut up one device, then the other one comes, and then Alexa tells me that she knows what to do.
All right. Well, I think we have time for one final question, Kurt. And that question would be, what do you think of application of machine learning in geophysical data? Is this the advanced step in terms of interpretation and modeling of hydrocarbon and geothermal reservoirs?
Oh, that's the wrong question. I consider that machine learning is a joke generated by Schlumberger for marketing purposes. We published papers on doing 3D inversion with machine learning in 1995 at the Washington, D.C. SCG. And some of the patents we did in this are already expired. So machine learning is nothing else than applying neural networks to save computer time and work with more data. When you work in the Barhole environment, we had 5 supercomputers doing exactly that 25 years ago. So it was actually Fred Amenzada who was calling me, and he was trying to push me on giving a machine learning talk or something like this, because he's also reliving his 20-year-ago book because it's now a fashionable thing. So this is 20 years behind reality. We can talk about machine learning, but it's really old stuff. So we have ways to do it and integrate it. We have patents in it. We've got procedures in it, how to apply it. It can be very helpful. But, you know, you need to have the money to actually do it. And it's just a marketing ploy to have the oil companies taking the drugs of the service company so that they only buy from one service company. Using neural nets and do machine learning and handling large data set is any geophysicist that has been working for 30 years in developing these techniques knows about it. So it's nothing new. It's just a fashionable thing right now, because there's nothing else that interests people that catches their eyes. So some big guy said, oh, we do this machine learning. So you asked me the wrong question.
All right. Well, I'll give you a better question to end this. I was going to end on that, but I'll give you an easy one. I'm curious how you got involved in geophysics in the first place, Kurt. How did you find geophysics?
I actually have a friend from high school listening to this talk, so he can check me. He's calibrating me. So we had a very lazy French teacher. His name was Koene, and the last few days before we had to select what we would study, he decided that his hobby was rocks and geology. Instead of teaching French, he took the whole class and we walked along a road up the mountain, and he showed us all the rocks and this and that. And then he says, now you have to fill out the forms, what you're going to study when you go to university. And this was a monastery school. So we walked up around that mountain. So he had a list, and on this list it said geophysics. I said, what's geophysics? He says, wait, I'll bring you a book. So the next day he gave me a book, Fisher's Dictionary of Geophysics, about 2 inches thick. And I read it and I really liked it. And then I took it back and said, I really liked it. I think I want to study that. And he says, you can keep the book. I still have it in the dictionary section of my library. So that's how I got into geophysics. And then I started building equipment. I wanted to be an engineer. My boss said, no, you're not. You're going to go to university. You're not going to be a stupid engineer. And when industry goes down, you're not going to have a job. You're going to study. And so I studied geophysics because that's what I selected. And I loved it ever since.
That's great. I like that story. All right. Well,
and I can be calibrated. I will get shit from my friend after this if I fly.
All right. Well, thank you, Kurt, very much for an excellent presentation. Thank all of you for attending the SEG Europe Regional Advisory Committee's webinar as part of our webinar series, Geophysics for Today and Tomorrow. Please look forward to our social media posts and check out SEG Live, which can be found on the SEG homepage for further opportunities to register for our webinars. Kurt's part 2 and part 3 will be posted shortly. Thank you all again for attending this webinar. Thank you, Kurt, for an excellent presentation. And I hope everyone has a great day. So until next time, have a good day. Bye-bye.
Thank you, Laurie, for
Thank you,
doing an
Kurt.
outstanding job setting this up.
Thank you. Bye-bye.
Bye.